students, welcome to the knowledge series. Here we are going to discuss on defuzzifications. I believe that you have gone through the earlier series on the defuzzifications with respect to the FIS I have discussed. Now here in the defuzzifications, what exactly it means? Defuzzification means it's the process of producing a quantifiable results in crisp logic for a given fuzzy set values or a corresponding membership degree. Actually, defuzzification it is the process that maps the fuzzy set to a crisp set, and this fuzzy set we get from the FIS. Immediately after FIS we get this fuzzy set, and that is being used to process through a defuzzification to get the crisp set. It is basically a fuzzy control systems that has this setup like a fuzzification, defuzzification, fuzzy rule systems and fuzzy inference systems, and thereby defuzzifications produce the crisp output. Now why this defuzzification is necessary? Because defuzzification, it is the conversions of the fuzzy control signals, and it is necessary because the actuators which is that needs the crisp signal has to get that signal after being defuzzified. So that's why defuzzification signal is important based on the given crisp input. So the crisp input and the defuzzified crisp output is both are interlinked based on the fuzzy concept. Now here we will be seeing different type of defuzzifications methods. Now some of the defuzzification methods I have put here is maximum membership function principle, centroid methods, weighted average methods, mean max membership, center of sum, center of largest area, then first of maxima and last of maxima. Let's see individuals one by one. Now the very first things we are going to see across this one is what maximum membership methods. Now it is mentioned here is that this method gives the output with the highest membership functions. See, highest membership function. This defuzzification technique is very fast, but is only accurate for a peak output. So here you try to see this one, the crisp elements, membership axis, mu, and this is the plot which is being given, the output plot, and here at the maximum peak, whatever we are getting, we consider that that peak as the crisp output. So the at this peak, whatever is the crisp output we are getting, that is the defuzzified output. So here it is being denoted in terms of a function. Mu a of x star is greater than mu a of x. That means any value of x as compared to the x star, it is smaller. So that's why mu of x star, this at this point the maximum peak you are able to achieve. That peak is has a the boundary limit is 1. So that is 0 to 1 is the maximum limit. So within that limit, whichever is the maximum, that is treated as the crisp output or the defuzzified output. The next is the centroid methods. Now the centroid method is the method known as the center of gravity or center of area of a defuzzifications. That means this is the another defuzzifications graph is being shown. Here wherever the center of the gravity in this given area is coming, that is being treated as the defuzzified output. And this was this was developed by Sugino in 1985, is commonly used and is very accurate because this is the centroid method is there. Now here we will divide this area into a various interval. When you divide this area, say for example from here to here one area, then from here to here there is another area, then another area between these rectangle, then another triangle. So there is one triangle, there is another triangle, then there is another square or rectangle, and then another triangle. So like that every interval we take it. So X star is a integration of membership functions of a given area, a membership function of a given area with respect to the X element divided by the total membership functions interval. So that is what we have defined here. So mu I of X, where AI is the center of the gravity. So X star is the defuzzified output and mu I of X is the aggregated membership functions, and X is the output variable. So we take the entire integrations. So entire integrations of the given area we are taking into considerations. Now another is the weighted average. In this method, the output is obtained by the weighted average of each output of the set of value. The weighted average defuzzification technique, this can be expressed as X star is equal to summation I is equal to 1 to n mu I of X into its weight divided by summation I is equal to 1 mu I of X. So in the previous case we have taken into consider at every stage of the elements, but here we are taking into considerations the weight with respect to the each defuzzifications weighted. So that's why it is a weighted average. So we are taking the average weight here. So weighted average of the set of rules. So this is given by the summation denote the total algebraic sum, and X star is equal to mu I of X into A, then mu I of mu 1 of X into A, mu 2 of X into B divided by mu I of X and plus mu 1 of X plus mu 2 of X. So that is exactly just like the centroid methods, but difference is in terms of a weighted. The mean max methods. This method also called as a middle of maxima, where the maximum membership function can be this maximum membership functions can be plotted except for a nonlinear locations. So if it is a linear locations, then it will be able to give the maximum. So that means that here if you try to see the maximum area, so in this particular point you have a maximum area you can able to visualize. Under that particular area you can observe. So this is this particular plateau or this particular plane, you can see that you are having a maximum membership function, and this plane we are taking the average. We are taking this area, and that area we are dividing to 2 half, that is A plus B divided by 2. So that gives the mean max membership. The next is the center of sum. This process involves the algebraic sum of the individual output fuzzy set instead of their union. The defuzzified output is nothing but, so here what we do is that we try to take into considerations the algebraic sum. So we take a first membership functions, we take another membership function, we sum it, and that one in terms of an integral we are taking into considerations. We can see some of these defuzzifications in terms of one example, and then we take integrals of the range X divided by the total membership functions, its integral. So that's how we can able to define the center of the sum. So here the center of the sum is nothing but this point, particular points, wherever it is having intersections. So this shaded area is the central points. So that is X star is being denoted. The next is the center of the largest area. When we talk about the center of a largest area in this method, the output is based on the largest area of the membership. So largest area, if you are having a number of areas, suppose this is one area, this is or else you take this one, this is one area, this is one. So we take into consideration the largest area of the membership value. So we take X star based on the integral of that bigger area membership into the element dx divided by memberships dx. So that's how we try to define the another way of center of largest area as a defuzzified output. Now lastly we are showing the first of maxima, last of maxima. In the first of maxima, that is FOM, that is means it is defined as the greatest lower bound, and in this one X star is given as infinite. X belongs to capital X, X belongs to small x, element is belongs to the universe of discourse. Mu I of X is the height of AI. So that means where INF is sorry, this is infirm. So this infimum that is indicates the greatest lower bound. Just like we have talked about a supreme is the least upper bound. So this is the greatest lower bound, that is infimum. This infimum of X belongs to capital of X. That is on the lower side, whichever is the greatest value, that is one. And here on the upper side, whichever is the least value, that is 2. So here first of maxima we take it to considerations. So suppose if you take the lower side is 0, so in the last we take it as 2. On the other side, if you are taking this, so assume that this is the last point, so we will take this one as the lowest supremum. So last of maxima is nothing but supremum. X belongs to X, element belongs to universe of discourse, where mu of AI of X is the height of AI. So that means we look for the lowest of the greatest upper bound. So that is the last upper bound. So which comes as the last of maxima. So this is how we can define the different membership function. Now let us see this one with one examples. Now if you try to see across this example, in this example we have shown that there are 3 fuzzy set is being shown. The output of each fuzzy set rules is in a particularly is shown like this one. Calculate the total output using a graphical approach and calculate the defuzzified using centroid method, weighted average and mean max. So we will see the one of the methods, and other is a self-explanatory. Now if you try to see this one, we take one membership functions, we try to create in the FIS systems. You can see that in the Mamdani case we have a 3 fuzzy plots, and we try to create the rules, and there after that after applying that entire rule, what we try to do is that we try to combine all these things together, and finally we create one output distribution. So this is the output distribution that you try to see here. So in this output distributions we have got this type of a plot. Now here what we are trying to do is, under the first case centroid methods and the weighted average, that are the 3 methods we are. So in this particular case, while solving, you have to be very careful in how these particular methods we can able to solve. So let's see the first case with respect to the let us take the case with respect to this particular mean max plot methods, mean of maximum methods. That is one, or we will go with the simple centroid methods to see that how this particular problem can be solved. Centroid method that will be enable you to give an idea, so that other things you can simplify it in an easy manner. Now here what we do is that, now first of all we try to take a range 0 to 1, and here this is the set region how we plot it. between 0 to 1 range, here you can see that mu of x, this is the slope line equations. In the slope line equation, x minus x1 divided by y minus y1 is equal to x2 minus x1 divided by y2 minus 1. Now here x is equal to z, this x is equal to z, and y is equal to what? Mu of z. That is why here written here. So here when you try to see the z is between 0 to 1, that is the range, and mu of z is how we represent mu of z is having a range 0 0 to 1 comma 0 3. 1 is here and this is 0 3, so this is the range. So you substitute this value of value across this one. So when you try substitute this value across this one, this is z, this is mu of z, and what is this x1 value? This is x1 y1, and this is a x2 y2. So you put the x1 y1 x2 y2, you get and finally this z and mu z is unknown, so that's how you get this value. Mu z is equal to 0.3 z. Now from here, next is coming from this point to this point. That is what the range is between 1 to maximum of 3.6, because if you see this point, the coordinate is 3.603. 3.6 is up to here and 0.3. So 1 to 0, 1 z is interval between 1 and 3.6. So what is the mu z value? Because here you are finding mu z is the vertical components. So here mu z is straightforward is 0.3. Now next is coming 3.6 to 4. 3.6 here and to 4. 4 is here. This is another triangle you can see, try to see. Now here again we are applying this membership, slope line equation. So this point is 3.603 and here it is 4 and 0.5. So you apply the straightforward this one. So what you write? You write z minus 3.6 and mu z minus what is vertically, it is written as 0.3. And what is the next x2 minus x1 y2 minus 1? That is 4 minus 3.6, 0.5 minus 0.3. And from here you get another mu z is equal to 0.5 z minus 1.5. Now next interval is what? After this one there is another square, you get it 405 to 5.6, that is 4 to 5.6. That is the interval. Z is between 4 to 5.6. So what is the vertical, what is the slope you are getting maximum? It is, you are getting 0.5. So that is mu z is 0.5. Lastly, lastly here next is you are getting 5.6 to 6. That is what here 5.6 to here. This is another triangle. Now here when you again you are applying a slope equation just like the previous case. Now here you will be writing z minus 5.6, mu z minus 0.5, then 6 minus 5.6 and 1 minus 0.5 c, and you get this value. This way, after doing this one, there is another square and another triangle. So that is what you can say. Square comes straightforward, and when it is a slope, then again you apply, you got it. So here what we do is that applying the centroid equations 0 to z 8, that is the what is the maximum range here? It is 0 to 8. Now in the 0 to 8 interval, mu z dot z dz and 0 to 8 mu z dz. So that's how it is. So we define this one is equal to, we break based on the interval we selected. These are the z, there are 7 combinations of the interval. So up to there are 7 these 7 combinations what we are writing: 0 to 1, 1 to 3.6, 3.6 to 4, 4 to 5.6, 5.6 to 3.6, 8 to 7, 7 to 8. So the numerator when you put it, we get it 18.25. And the denominator part in the similarly 0 to 8, and we are putting all these 0 to 1, 1 to 3.6, 3.6 to 4, 4 to 5.6, 5.6 to 6, 6 to 7, 7 to 8. So that is how here. So when we put it, we get 3.64. Now this total values of this one divided by the numerator and denominator, if you substitute and divide, we get it as 5.01. So this is known as the centroid method. This is this needs a lot of work. Now the another is a weighted average. So we try to take the average with respect to the different sections. So that is 2.5 into 0.3 5 into 0.5, then you take into 6.5 into 1. So that's how we try to look for the we take the central point, and then we try to take the 1.5 and 0.3 is nothing but is the membership. 2.55 and 6.5 is the midpoint. We try to take it. That's how the weighted average. Here I have shown here 0 to 5. So 5 plus 0 divided by 2, so that is 2.5. 3 to 7, so 3 plus 7 divided by 2, 5 you got. 5 to 8, 8 plus 5 divided by 2, so that is 6.5. So that how we divide this entire regions from entire distributions. We try to put across this one. This is one distribution, this is another distribution, this is third. So with this we try to create a weighted average, and finally the mean max. Mean max is taking, if you are taking the two regions and putting together. So this how we solve the problems, and there are several other examples are available. You can go through the various examples, even refer to the notebook. You will be able to get the idea about how we solve this maximum, minimum, weighted average centroid methods. So this covers the defuzzification's various methods. Every method has a different examples. Please carry on. So the defuzzification's output will produce the crisp output, and that crisp output is the output which we finally use to process the actuators. So with this I conclude. Thank you.